So we're going to continue on with our assignment or our example. A sub s is equal to 1.32 square inches. B is equal to 8 inches. D is still 16, which is h minus the cover. And rho is equal to AS BD over BD, right? AS over BD. 1.32 square inches divided by 8 multiplied by 16. And what does that come to be? 1.32 divided by 8, 16 is 0.0103. Do our check. And our check is rho min is 200 over f sub y, which is 200 over 60,000 is 0.0033. Rho is greater than rho min. That's good. Rho max is equal to 0.01806. And of course I could show you the equations for that value, or you could just look it up. 4,000 psi concrete, rho max, looked up on a table. This table will be in your examinations. So you check that. Well, rho is less than rho max. Okay, if that's true, then we are in tension control. Phi is equal to 0.9. A is equal to AS F sub y divided by 0.85 F prime CB, which is 1.32 multiplied by 60 divided by 0.85 F prime CB. B is 16, right? F prime C is 4, and B is 8, stupid. And if we go through that, we get that A is equal to 2.91 inches. Nominal moment capacity is A sub s F sub y multiplied by D minus A over 2, which is equal to 1.32 square inches multiplied by 60 kips per square inch multiplied by 16 minus 2.91 over 2. This comes to be 1,151.9 kip inches multiplied by 1 foot divided by 12 inches, and that gets me a moment capacity of 96 kip feet. I have two significant figures because I only know my other values to two significant figures. So that's how we do an analysis if the beam in Ender analysis is adequate or inadequate. Of course, there's a limitation, right? Once we have rho max as our reinforcement ratio, we end up in a position where we cannot increase the capacity of the section unless we increase the capacity of the concrete, and sometimes we can't do that. So in those cases, we have to treat our concrete and doubly reinforce it. And this is what we've been doing most recently. A doubly reinforced beam consists really of two beams, one that has a concrete compression block and a steel tension block, plus one that has a steel compression block and another steel tension block. And they're both in the same place. And so now we need a few more vital statistics to look at. So let's take a look at how we would perform that type of analysis. The first thing that we would do is we would go on and look at our beam. So let's take a look at a doubly reinforced beam. This one here has some steel at the base. It has some compression steel. It has a depth H. It has a width B. The depth to the reinforcing steel at the top, or the compression reinforcing steel, is D prime. We know the concrete is F prime C. The steel is F sub Y. We have to check two things. First is that rho is equal to AS over BD. The second, rho prime, is equal to A prime S over BD. First check, rho has to be greater than rho min. If not, the beam is inadequate. Fail. If so, we have to check if rho minus rho prime is greater than or equal to K, which is equal to 0.85 beta 1 F prime C over F sub Y D prime over D multiplied by 87 divided by 87 minus F sub Y. If rho minus rho prime is greater than or equal to K, then the compression steel yields. What does that mean? That means that A is equal to A sub S minus A prime sub S, F sub Y, D minus A over 2. That's the first beam. Plus, A is equal to A sub S minus A prime sub S, F sub Y over 0.85 F prime CB. That will spit out a value for A. We check if rho minus rho prime is less than rho max, then we're okay. If not, the beam fails. It's not in tension control anymore. We compute our moment capacity. If it is true, then phi is equal to 0.9. And our moment is equal to AS minus A prime S, F sub Y, D minus A over 2, plus A prime S, F sub Y, D minus D prime. And as usual, design moment is our production factor multiplied by our computed moment capacity, or nominal moment capacity. If, on the other hand, rho minus rho prime is less than K, then the compression steel does not yield. Which means that F prime sub S is not equal to F sub Y, and but F prime sub S is less than F sub Y, and we can go on from there. If that is true, we solve for C from the equation A1 C squared plus A2C plus A3 is equal to 0, where A1 is equal to 0.85 beta 1, F prime CB, A2 is equal to A prime S multiplied by 87 minus 0.85 A prime S F prime C minus A sub S F sub Y, and A3 is equal to negative 87 A prime S D prime. Those of you who are in the Tuesday class, when we derive this, we missed the prime. That's why our numbers were so funky. So that is the correct equation. And then, once we know that, we can calculate that C is equal to minus A2 plus or minus the square root of A2 squared minus 4A1, A3, all over 2A1, which gives us a solution for C. We check that the strain in compression in the steel is equal to 0.003 multiplied by C minus D prime over C. Or we can compute, and this must of course be, has to be less than the yield strain, or we can just go right ahead and say that F sub Y is equal to 87 C minus D prime over C, must be less than F sub Y. Sub Y, check that, and if that is the case, then we have our nominal moment is equal to AS F sub Y minus A prime S F prime S multiplied by D minus A over 2 plus A prime S F prime sub S D minus D prime. Remember that A is equal to beta 1 multiplied by C. And so you then, since rho minus rho prime was less than rho max, phi is equal to 0.9, and our ultimate moment is phi m sub n. And that's a complete solution. So I'm going to stop this recording now. We're going to pick up and we're going to do an example of a doubly reinforced section.